the Earth's natural cooling system. It's in trouble. And the result? An alarming increase in global warming and climate change. It is hard to solve any sort of problem just by learning and repeating a catchphrase, as in the phrase global warming. It's a warning, but it's not an explanation. In this video, I explained the Earth's natural cooling system and how it has been weakened by rising levels of carbon dioxide. Let's begin with two scenarios for how well the Earth's natural cooling system might be working. Scenario 1. When the Earth's natural cooling system is working properly, the Earth successfully sheds into space just as much heat as it takes in from the sun. Result? The average temperature of the Earth remains the same. The Earth doesn't get hotter, it doesn't get cooler. Scenario 2. Our Earth's natural cooling system becomes compromised. Our Earth's heat-shedding capacity slows down. On a daily basis, the Earth no longer sheds quite as much heat as it receives from the sun. Result? With its cooling system weakened, the Earth's average temperature begins to climb. This second scenario, that the Earth's natural cooling system won't keep up, has been with us for some time now, which accounts for the emergence of global warming as a dangerous trend. The proper way to explain this development is to characterize it as a weakening of the Earth's natural cooling system. To understand what's actually happening, we need to familiarize ourselves with two central topics, photons and the Earth's atmosphere. Let's start with photons. Photons are weightless particles of energy. They always travel at the speed of light. Although it would be just as accurate to say that light travels at the speed of photons because light is nothing more than a steady flow of photons. What matters to us here are the photons produced by the Earth, as all its warm surfaces cool themselves by doing what? By converting their heat energy into a steady flow of photons. This flow of photons races into space. This flow is the heart of the Earth's natural cooling system. It's how the Earth removes heat from its surface and gets rid of it. It's an endlessly repetitive process. By day, the sun's photons warm the Earth, and both by day and by night, the Earth turns the energy it receives from the sun into a new round of photons, which then get fired into space. Sun's photons in, Earth's photons out. This is the Earth's natural cooling system. The sun's photons, i.e. sunshine, are quite intense. They're short wavelength bundles of energy, vibrating at frequencies that the human eye can see. The Earth's photons are not as intense. They are lower frequency, longer wavelength particles of energy vibrating at infrared wavelengths the human eye never sees. Infrared scanners do see them. Think of the scanners used by police helicopters for tracking fleeing suspects at night. After an entire night of shooting photons into outer space, the Earth's night side becomes much cooler. When I first invited you to learn the basics of the Earth's natural cooling system, you might have said, huh? But now you can say, yeah, I get it. The Earth does have a natural cooling system. Before we humans acquired our knack for industrialization, the Earth's natural cooling system was effective enough to keep the Earth's temperature somewhat stable over long stretches of time for many, many centuries. Now let's switch from photons to a new topic, the Earth's atmosphere. Why do we care? Because the chemical composition of the Earth's atmosphere directly affects the success or failure of the Earth's natural cooling system. The atmosphere mostly consists of simple molecules, nitrogen, N2, and oxygen, O2, plus individual atoms of argon, Ar. These gases make up 99.93% of the atmosphere, or so we are told by Wikipedia. But the atmosphere also contains complex molecules, i.e. molecules that contain two different elements. For example, carbon plus oxygen, or CO2, known as carbon dioxide. Carbon plus hydrogen, CH4, methane. Hydrogen plus oxygen, H2O, water vapor. Others refer to these molecules as greenhouse gases. For now, let's just refer to them as complex molecules. What's important about complex molecules? What makes them different? On the simple side of the atmosphere, atoms of argon and molecules of nitrogen and oxygen never snap up any of a cooling Earth's escaping photons. But complex molecules regularly capture a portion of the Earth's escaping photons. This capture will happen whenever there's a match between the photon's frequency and the capturing molecule's energy bonds. When there's a photon-to-molecule match, the molecule captures the photon and converts its energy instantly into molecular energy, i.e., into heat. The moment this happens, the photon ceases to exist. The capturing molecule then shares its added heat with whatever molecule it bumps into next, most likely a molecule of nitrogen or a molecule of oxygen. What shall we call all those photons that get themselves captured by the atmosphere's complex molecules? Let's call them photons captured. So here's the larger picture. Most of the photons created by the cooling of the Earth's surface will vibrate at frequencies that don't interest complex molecules. Such photons will therefore make a clean getaway through the Earth's atmosphere and speed off into space. And what shall we call all these photons that zip through the atmosphere without being captured, taking bits of the Earth's heat with them? Let's call them photons escaped. Note, photons escaped cool the Earth by removing energy from the Earth's surface and transporting it through the atmosphere and off into space. Add together all the zillions of photons escaped, and what they give us is the Earth's natural cooling system at work, the Earth's natural cooling system doing its thing. But photons captured, by contrast, merely move heat from the Earth's surface into its atmosphere. From photons captured, the Earth derives not a smidgen of cooling benefit whatsoever. All this implies two different scenarios for the fate of the Earth's natural cooling system, a stable scenario and an unstable scenario. The Earth's stable climate scenario. The photons escape percentage remains high and stable, and these photons carry away just as much heat every single day as the heat the Earth has already received from the Sun. In the stable scenario, the Earth's natural cooling system is in good working order, and the Earth's average temperature is steady. Glaciers don't shrink, hurricanes don't become unusually destructive, forest fires don't become scorchingly disastrous. In the Earth's unstable climate scenario, greenhouse gases accumulate in the atmosphere, and we get a new normal. Solar heat in, constant, photons captured, that percentage rises, photons escaping, that percentage falls. The Earth's natural cooling system loses ground. Our Earth becomes warmer and warmer and... Now to the data. How much carbon dioxide have we added to the atmosphere? How fast is the Earth warming? Let's have a look. Atmospheric carbon dioxide rose from 280 parts per million in 1764 to 316 parts per million in 1960. Almost 200 years later, a rise of about 13%. And now, in 2020, atmospheric carbon dioxide is at 412 parts per million, a total rise of 47%, and most of that rise coming in just the last 60 years. Scary fast. So what? Has all this new carbon dioxide made a real difference? Is the Earth getting measurably warmer? Turns out the answer is yes. In the next few slides, we will take the temperature average for the entire 20th century as the zero line on the graph, the solid line near the bottom. The 1880s and the 1890s were both about 0.2 of a degree Celsius below the 20th century average. The 1940s, 1950s, 1960s, and 1970s were all very close to the 20th century average. In the most recent 4 decades, we have begun to see global warming really begin to take hold and take off. From here forward, let's acknowledge our unwitting error. It simply didn't occur to us that our Earth might have a natural cooling system, nor did we realize how much damage we were doing to our Earth's natural cooling system. So now it's time for a handyman's revolution, i.e., a handy person's revolution. in which we replace all the household gadgets that now run on fossil fuels with new household gadgets that just use electricity. And it's time to do much the same for how electricity is generated, how industries are run, and how vehicles are powered. In other words, it's time to replace fossil fuel technologies with climate-safe technologies. The faster we get there, the better off the Earth will be, the better off humanity will be. Right now, the Earth's natural cooling system isn't doing its job because we won't let it. Bending our civilization toward a relentless weakening of the Earth's natural cooling system is not safe. The Earth's natural cooling system is precious. We need to give ourselves a civilization that relentlessly protects our Earth's natural cooling system. Thanks for joining me on this search for clarity. To ask questions, give feedback, or just learn more, visit my website, AmericaUnstuck.com. I'm Steve Johnson, former cab driver and union president, MBA, management consultant, independent researcher, and my motto, it is by accepting and fulfilling our higher responsibilities that we will earn our higher freedoms.